I'm Bhavidhir V. Bharadwaj. Welcome to episode 11 of Genesis of Tomorrow. The following is a conversation about ultra-cold atoms, quantum gases and superfluids, atom interferometry, spectroscopy, quantum criticality and more with Dr. Saptarishi Chaudhuri, an experimental physicist, principal investigator and researcher at Raman Research Institute, one of India's leading research institutes in the domain of physics, with his PhD from Tata Institute of Fundamental Research and prior research experience as a researcher at the National University of Singapore. Also, 86.1% of you watching this have not subscribed yet. If you get even the slightest bit of value from our show, please support us by clicking that subscribe button so that we can keep improving the quality of the episodes and keep on bringing such wonderful guests over for you. And now, without any further ado, let's get right into it. Enjoy and thank you. First of all, what are ultra cold atoms? A basic
Okay,
explanation regarding it, right? Uh, what they do, how the techniques that are used take them to those minute and absolute zero nanoscale temperatures. So, how does it all work?
okay. This is a fairly recent technology of laser cooling and trapping of neutral atoms. So typically, what is done is that at room temperature, all around us are these atoms and molecules. Even we are breathing this air molecules, which is consisting of oxygen, nitrogen, and so on. And at this temperature, which is typically, let's say, we are at 25 degrees centigrade, which is very close to what is known as 300 Kelvin temperature scale. These atoms and molecules are moving with an extremely high velocity. Their average velocities are of the order of several hundred meter per second, and they can even go up to kilometer per second. Now, one of the difficulty with these fast moving atoms and molecules, if you want to study their property or you want to use them for any precision measurements, they just fly away extremely fast. So you have limited observational time. You have effects which are mostly classical physics dominated. So all the quantum properties of these atoms and molecules are typically not observed because of this high thermal motion of them. So there is this technology of actually reducing their motional velocity to extremely low level, and by reducing their velocities and speeds, you can actually also reduce the distribution of their velocity. And in kinetic theory concept, so that is like reduction of the temperature of that gas of atoms and molecule itself. So how do we do that? So first, now that we are clear about the motivation why we need to do that and so on, and what is done is that we use lasers to actually reduce the velocity of this atom. So just imagine an atom which you can think of a billiard ball at very high velocities, has energy levels from one energy level which is typically known as ground state. uh, it can get excited to a higher energy level which is an excited state. Now this two level atom or two level approximation of this atom, this can absorb a photon if the photon is directed towards the atom, and this photon is generated from the laser. And while absorbing the photon, it not only goes to the excited state, I mean the atom not only goes to the excited state, it also absorbs an unit of linear momentum from the photon. And that means dividing that linear momentum by the mass of the atom, this much velocity change will happen to the atom. Now imagine that the photon is very carefully directed exactly opposite to the motion of the atom, then its velocity will get reduced in that direction. Okay, so that is the very basic idea of reduction of velocity by absorbing a photon. However, you can then ask that photon which excited the atom eventually has to leave the atom via a process called spontaneous emission. But the spontaneous emission now happening in all random direction, many spontaneous emission cycles will actually give this small ever so little momentum jitter which is in all random direction, and this will eventually get averaged out to zero. Whereas the direction of the velocity change it actually encountered because of the absorption of photon which was coming from a particular direction which the laser had sent actually causes the velocity to be reduced in that direction. Okay, and then something more clever is done. The laser frequency is kept slightly below the transition frequency between these two levels of the atom. By doing so, what happens, only an atom which is moving towards the laser will see the laser frequency Doppler shifted to be on resonance or close to resonance. The Doppler shift, the same concept what you are familiar in terms of sound, the motion of this atom is now apparently makes the frequency or the color of the photon to be shifted up, and then only atoms which is moving towards the laser is getting this photon for the reduction of the velocity. So this is how in one direction the velocity is getting reduced. Now the arrangement is made in such a way that the laser light is targeted from both the positive direction and the negative direction, so that an atom which is moving either to the right or to the left, it feels a motional damping of its motion because of the scattering from the laser in the both directions, so it gets its velocity reduced whether it wants to move in the left or right, and then you can easily extend this concept to up and down and forward and backward. So typically laser light is sent from 6 direction, and the region where the laser light, it's not just a very small sized beam, it's a reasonably large sized beam, reasonably powerful in terms of intensity of the laser. There is a region in which whatever atoms are there, their velocities gets reduced now, and it's very surprising that this single process takes down the effective temperature to something of the order of a microkelvin temperature. So this is a number which is like 10 to the power minus 6. That means typically between 8 orders of magnitude or 7 to 8 orders of magnitude below the temperature in which these atoms actually are held at present. So it's a huge reduction in terms of temperature. So that's in a nutshell what is known as so-called Doppler cooling. Then there had been a lot of progress in the field. People have realized that after cooling these atoms, they can be trapped in space by use of an inhomogeneous magnetic field. These atoms are typically can be thought of tiny magnets. Most of the atoms have their ground state energy which is proportional to a local magnetic field, and the energy gets shifted depending on the local value of magnetic field according to a principle which is also known well to the audience, I guess. It's called Zeeman effect. And then if you create spatial inhomogeneity or spatially varying magnitude of the magnetic field, you can create a region in space where the value of the magnetic field is such that the energy of the ground state or the Zeeman shift actually takes these atoms to the lowest possible energy state, and atoms tend to accumulate in that space, and we call such atoms low field seeking states. And then there is a trapping of these atoms after this so-called Doppler cooling. And in a technical sense, these two processes of optical, that means using lasers to cool atoms, and magnetic trappings are combined together, and then this is famously known as magneto-optical trap. And at one point, the light which is actually cooling these atoms, they are switched off because their purpose is served. The atoms are already cold enough, and then these atoms are held in space in this magnetic field itself. And then there is an additional technique of finding the higher energy of atoms among them, among those bunch of atoms which are already trapped and cooled, typically ranging from few millions to even a billion atoms. And the higher energy ones are selectively thrown out of the trap, and this selective throwing out of the trap is very similar to the way you cool your coffee cup. Means when you actually blow out the upper surface of your coffee which is hot, then the remaining coffee in your cup eventually gets even colder, right? So if you can actually blow out, this blowing out is done by something called a radio frequency field, which is also generated in the laboratory. Then the remaining atoms are cooled down below microkelvin temperature scale. They go down to of the order of nano kelvin temperature scale, or 10 to the power minus 9 level of temperature, very very close to absolute zero. And such low temperature cloud of atom typically is known as ultra cold atoms. And in that case, one very interesting phenomena emerges, that each atom is now no longer to be thought of as a billiard ball. They behave like a wave. So there is a wave property of this atom which emerges, and then a wave of an atom tends to overlap with a wave of an atom which is next to it, and another one which is next to it. And then all these waves, once they overlap, of course there are certain conditions they have to follow. For example, these atoms have to be bosonic species, they can't be fermions, because then the wave tends to not overlap. They actually fermions do not like to stay together. But if they are bosons, then this overlap of these waves or atoms leads to something known as Bose-Einstein condensation, which was kind of predicted nearly, not nearly, exactly 100 years ago by seminal theoretical work by Indian scientist Satyendranath Bose and Albert Einstein, and which led to the development of statistics known as Bose statistics, Bose-Einstein statistics. And then also Bose-Einstein condensation is one of the fantastic demonstration of these statistics. And in modern times, this ultra cold atom cloud or this Bose-Einstein condensates are used for many many practical applications, which we will discuss along the way. So this is in a nutshell how this technique is done. So, if you have questions, you can ask.
I was really looking forward towards touching this matter of Bose-Einstein condensates, but you already talked about it in a very thorough manner. However, before we move forward, one thing that I would like to ask you is, how does this interaction of a multi-atom system or a multi-body, when we study
Hmm.
multi-body physics,
Correct.
And in
Many
regard to
body physics.
yes, many body physics, in regard to cooling them down and probably utilizing them in quantum computers as qubit technologies, how does that work? And could ultra cold atoms, this technology, be a more viable option than the other qubit technologies like trapped ion or superconducting ones?
Okay. So, the second part of your question is relatively easy to answer. So, it depends, for example, which particular platform uh, is to be considered as a more viable option for doing quantum computation. And this depends a little bit on the context. For example, there are multiple technologies which are at a matured level now. For example, superconducting qubits, you mentioned trapped ion qubits, and there are also photonic systems as well as semiconductor spin systems and ultra cold atoms. And all these platforms are providing some advantage or other depending on the uses. And this is a question I hear very often: which platform will be the most suitable and which platform will be chosen? Uh, the answer, as far as I am concerned, is that there is no need to perhaps focus on one platform over other at the moment, because at the core of the processes getting done, that means quantum computation, logic operations, etc., uh, almost all these platforms are providing excellent solutions. And there are many emerging platforms which are coming up. So it's a nice time to do physics, particularly quantum physics, where the same operation could be done using multiple platforms. I would rather say that instead of focusing on which platform offers an advantage, it's perhaps better to discuss about how these neutral atoms can be employed for getting the quantum computation related tasks done. So one of the pathways which quite a few groups have taken in recent past, including ours, is that to trap these atoms in what is known as optical tweezers. So this is another concept which I did not discuss before, is that if you focus reasonably high power laser light at a extremely small area using a strong or large lens, then what happens is that the intensity of the light varies over space pretty steep. And then there is another concept which is known in the context of atom light interaction. The energy levels of an atomic system shifts as a function of the atom light interaction strength. So, where the intensity is maximum, the shift of energy level is also maximum. This is known as light shift or AC Stark shift. Now, you can use this concept to create a potential for these atoms where a single atom can be trapped inside such a steep focus. So one single atom, when it is trapped, and multiple research groups in the recent past have shown a single atom trapping using this focused light, then this single atom can be manipulated. For example, its state can be manipulated. The population can go from one state to another in a controlled way, and it can also be detected in a controlled way. So for example, you can prepare state and you can detect a state, and this is all you need to get certain quantum logic operations done. And moreover, you can actually make sure that you can not only trap a single atom in one trap, you can have another focus trap just next to it. By doing that, you can even create entanglement between these two atoms by some other optical excitation procedure. Specifically, in this case, we call it Rydberg excitation, exciting the atom to a very, very highly excited level. And then such a Rydberg excitation between the neighboring atoms causes a entanglement to be prepared, and this entanglement can be used for getting many quantum logic gate operations done. And in the recent past, few of the research groups, including few of the companies, who have demonstrated that neutral atoms can be used to do this kind of quantum logic operations, and practical quantum computations can be done using it. So there is a lot of excitement in the field that within the next few years, one can have practical quantum computer devices made out of these neutral atoms trapped in array of these tweezer traps. Another advantage is that since laser cooling and trapping technique naturally yields a large number of atoms at a very low temperature simultaneously, you can actually make multiple copies of these tweezer arrays and scale it up with a very large number of so-called single atoms in traps or physical qubits. And once you do this scaling up, the cost of scaling up is not as much as scaling up, for example, solid state system or a superconducting qubit system, where in order to go from 10 to 100 to 1000 qubits, it's enormous resource which one has to spend. Here, just by constituting a larger number of atoms in the array of so-called optical tweezers or dipole traps, allows you to do this scale up. So that is one of the most promising direction, scaling the number of qubits in this neutral atoms system, which is not necessarily possible in many other platforms. So this is one advantage and future promise. However, the challenges of doing so-called error-corrected quantum computation using a large number of physical qubits and making sure how many of these qubits are actually usable qubits for reliable quantum computation. So those are the present challenges which are being resolved. And if you follow this field of research using neutral atoms for quantum computation, the progress have been really breathtaking, and nearly every month or week we are getting newer and newer insights. So there is a good hope that this technology is maturing fast enough so that one can have this practical deployable quantum computation devices. Of course, I must tell you some other part of the story. These atoms, when they're trapped and cooled and their states are manipulated for quantum computation, etc., they need to be inside an ultra high vacuum atmosphere, because you don't want any other thermal atom to just knock them out of the trap. So these experiments are done inside an ultra high vacuum chamber, and which is an additional level of technical complexity, which most of the or all the labs working with ultra cold atoms are capable of doing that. So in order to have multiple copies of this ultra cold atom based quantum computer, so ultra high vacuum technologies for every user, that needs to be accessible first of all. And second demanding resource is of course the lasers. And here we are talking about lasers whose frequencies are precisely tunable and stabilized. So we do techniques known as ultra stable spectroscopy to actually lock or stabilize the frequency of the laser, and then send this stabilized laser to the ultra high vacuum chamber, where only the atoms we want to trap and cool, they are kept in a vapor form, so that this can be done. So there are technical issues, but most of the labs who are taking care of this kind of experiments, so they are capable of doing this technical challenges. In India, there have been quite a few labs where this ultra cold atom related research have been progressing for many years now, and most of the focus have been to explore fundamental physics. But in recent past, there is a significant amount of effort which is given towards the practical scalable quantum computer development, and one of these effort is visible in terms of this national quantum mission, which is announced in the beginning of October. And some of our research groups are actually working towards developing these neutral atom based quantum computers, as well as ion trap based quantum computers together. So for example, we have a consortium model where my research group at Raman Research Institute and research groups in other parts of the country, namely ISR Pune, IIT Kanpur, IIT Roorkee, NISA Bhubaneswar, IIT Guwahati, and IIT Patna. Uh, they are all working together to actually develop this technology for the country and for the users in our country. So this is an ongoing effort which is going on through the support of National Quantum Mission, Department of Science and Technology.
Before I go on to talk to you about other theoretical matters in this discussion, you are an experimental physicist,
Yes.
right? What, according to you, is the greatest or one of the greatest pain points or challenges that you have to tackle or face as an experimental physicist on a day to day basis?
So I think it's not particular to me, but in general, the challenges of experimental physics, especially the precision experiments globally, is that there had been a lot of development, particularly over the last 4 or 5 decades in technology. So one of the challenge is to be at the level of state of the art, because if you are delivering as an experimentalist, and if you are not working with the instruments which are state of the art, which is also extended to the idea of infrastructure. That means, how good is the workshop, electronics, and so on. So then things becomes a bit challenging. So, however, I'm very happy to see that the technical challenges um, in very high quality experiment in India is getting resolved nowadays. I can't talk about all fields, but at least I can say about the research field in atomic, molecular, and optical physics, where I see that it is becoming easier. Another challenge which I kind of faced when I was building my laboratory was the challenge of procuring funds, because if it is blue sky research, then it is always difficult to arrange for the funds, whatever is the
What is
proposal.
blue sky research?
So a blue sky research, I would explain in terms of which is totally curiosity driven. So
Oh,
that
okay,
means
right.
if you have a research for the sake that you are convinced that this research eventually will lead to something nice,
Right.
but it's very difficult to convince everyone. But on the other hand, if you happen to demonstrate, or if you see that there is a growing interest in the larger community, that the experimental research is towards developing viable technologies, then I am seeing that there have been a lot of support from the government in the recent past. That means not just Department of Science and Technology, other departments of Government of India, who are actually providing financial and funding supports, which is very nice. But this has been a challenge. It's not that it was not a challenge, but it is slowly getting resolved. And I'm hoping that with industry joining in, situation can only improve. But some other challenges which will probably take longer time to get resolved is the challenge of skilled manpower, because the idea here is that it requires an investment from the perspective of younger generation. For example, if a student who has completed their masters, or BE, BTech, and then expecting that within 3 months or 6 months he or she will become so skilled that the results what one expects to achieve in the lab will come, that is not always true. So it typically takes something between an year or two for the PhD candidates to actually become extremely comfortable to start contributing towards development. But this year or two is something which is not a wasted year. This is the time when one needs to work the most to get the skill, concepts, everything developed. So now, I think the challenge would be that if not all, most of the younger generation people should actually take up this challenge, so that there will be a good amount of skilled manpower. Eventually, at the end of the day, there can be a large number of instruments in the laboratory, but if skilled people are not operating those instruments, then it makes practically no sense. So that is why this challenge needs to be resolved, to make sure that there are enthusiastic people who are willing to invest their time and effort, so that they become skilled. And then everyone, I have seen by personal experience, that once people develop this comfort or the skill, then they really do wonderful research. So that stage is one of the biggest challenge. So apart from this, about having a skilled manpower or human resource, and funding, and having state of the art instruments, etc., I think the other challenges are pretty similar to any other field. For example, if it is a procurement of the instrument, it takes time, but those are not challenges particularly to the one area or other. Okay, so this is what I wanted to Hmm. Yeah.
You
Uh,
talked about a skill set and skilled manpower quite a bit.
hmm.
Apart from subject competence, are there some other skill sets or in general know-how that you feel that researchers or potential or aspiring researchers need to imbibe or cultivate in themselves?
Yeah, so particularly in experimental physics, what I mean by skill set is not just the knowledge about the subject. So that I'm sure our university system and IITs and ISRs are very good in providing, and I'm sure that many other places in our country the level of education is pretty high to provide the theoretical understanding or how something works. But one thing which perhaps younger people should particularly look for is an opportunity to really do hands-on practical research in the laboratory. And by that I am not meaning that only the laboratories which are part of their graduate coursework or their BSc or MSc laboratory. Definitely those things needs to be done, but one gap area what needs to be bridged is that even during the um, B Tech, MSc, even undergraduate studies, there should be some exposure to the research level laboratories where one can actually go see what's going on, and if possible to get an idea that what it really requires once you will become an independent researcher. So that is one area which is more of a personal interest which everyone has to take, because it's very difficult for an institutional level to provide that kind of facilities, because there might be a 60 student classroom. Not all 60 is particularly interested in having a career in experimental physics. So if the institute say or kind of forces all 60 of them to actually get the hands-on experience in a research laboratory, this may not be the right thing. But the ones who are particularly interested in that classroom should actually try to find opportunities so that they start to get the feeling for how to get involved with research at a level of where people are um, kind of developing newer technologies, producing experimental results which is inspiring development of new theory and so on. Because again, at the risk of repeating myself, the theoretical knowledge or the theoretical research is uh, is perhaps doing fine, means but they require something more to actually be able to produce rather than to remain as a user. Because at the end of the day you need to have things, technology, or even if it is some facilities, platforms which needs to be developed. It can't be that you know how it works and wait for someone else to make it for you, or you will buy it, because then this cycle will go on. So that requires a different level of training, and that has to come from within. Means it's very hard to actually create a uh, coursework for that.
I completely agree with that, Dr. Chaudhary. Further, one has to really be proactive in gaining this first hand hands-on application side of things.
Correct.
If I want to become a quantum engineer or I want to do research in X or Y field, it's better that when I'm in the initial years, like when I'm doing my undergraduate, as you said, because people generally have a lot of time at their hands. Even high school students, a
Yes.
student who's in 12th has a basic understanding of how science works, right?
Correct.
They can very much, and especially in today's time when accessibility is so high, you can
Mhm.
contact a research lab, a professor or a researcher, and ask them that I would like to visit you and I would just like to be under you for a week and just see how things work. And umpteen times when you do that, it would not only be a transformative process for you today, but actually for you in the longer run.
Right.
Because it's one thing to even watch a YouTube video with animations of how so and
Yes.
so is operating, but it's an entirely different thing when it's right in front of you. All the apparatus and the modus of operandi, they are set up in front of you and you're seeing how these lasers are working, how atoms are being cooled down, all of it. It's a completely different experience.
No, absolutely, absolutely. So the point what I wanted to tell you is that imagine that someone sees an YouTube video or attends a lecture, you will only hear about what worked. For example, when I am giving a talk to you, or I am telling you how this is done, if I share results which I published, let's say last month, you see that after an enormous effort, after enormous failures, what actually worked. So most of the theoretical research, when a student is presented with a particular equation and then its solution, so not just ours but everyone in the world, the results which are presented which actually worked. So that means there was no way for the particular student or the young researcher to know that how it actually worked. That can only be learned if you actually do that thing. For example, you might be very excited to say that, oh look, I could solve that equation today, which kind of required me to make those substitution, which was really nice, and so on. But at the end of the day, that is because the equation was given to you in that form, that was solvable or something. But in the real life experiment, when this is done, there is no equation, there is no solution which was presented to you. So one needs to know that how to actually know how things work from the perspective of making things work rather than just to know how things work. So I totally agree with you. So those how things works kind of YouTube videos or lectures or classrooms and so on, they have their value, but then there is something beyond it which is what actually is required. And so that is how I think the students need to. That's why I love experimental physics, because though it presents me on a daily challenges, and a lot of time nowadays I see my students who face those challenges, and then when I am spending time in the lab, we sometimes together solve the problem, sometimes they themselves solve the problem, and this gives you a certain level of pleasure, because once those solutions are found, those are not the same solution which were found or written in a textbook or something like that. Those solutions are actually leading to a new set of knowledge base, and that is the most fulfilling part of the work, which perhaps just reviewing what is happening will not give you that opportunity. That doesn't mean that you should stop reading or attending lectures, because that is the essential part which is required to reach a level, but there is something which is beyond, which needs to be taken care of.
What has been your journey, what has been your journey in regards to your interest or your inclination towards experimental physics? I'd more so call it the love for the subject, because as you're talking about it, it's apparent that, right, you have this passion for it, your
Yeah,
research and
so
whatever. How did you develop this?
yeah, so I'm very fortunate to have done my PhD in a laboratory in what is known as Tata Institute of Fundamental Research, TIFR, Mumbai, where we had the opportunity of working with state of the art facility development, I would say. Again, means I had the opportunity of developing the experimental infrastructure which produced the first Bose-Einstein condensate in India, and that actually gave me a lot of satisfaction. That was a significant part of my thesis work. And then I was very fortunate to have done postdoctoral research in a place called École Normale Supérieure in Paris, France, where a lot of ultra cold atom related physics development had happened in the past. So the laboratory where I was working, it was very famous laboratory for doing research related to ultra cold atoms, ultra cold fermions, and then bosons, and so on. Then I had another opportunity of fairly long term postdoctoral research in University of Florence in Italy. And so these three, and then I spent some time in National University of Singapore, nearly a couple of years. So all these places where I worked with this laser cooling, trapping, and quantum state manipulation of these atoms and molecules, so gave me this opportunity of learning the technology closely, and gave me an opportunity of facing the day-to-day challenges of doing experimental physics, along with the theoretical work which is kind of used for explaining the experimental results. And I did never think particularly which incidents would have made me having that much interest in experimental physics, but all these experiences have definitely helped me towards this interest and passion about experimental research, not just cold atom, but in general experimental research in the field of atomic and molecular and optical physics. But so this is so it's important, of course, where you are getting this opportunity. But often a lot of time is that every place will provide certain basic facilities, and one can look at it as a facility to get the work done for their job, and that will not develop that passion, is what I feel. So there is another thing what I learned is that there is nothing called someone is very good, someone is not so good. Means everyone is very good. Means only thing which separates between one person and another is this interest or curiosity to do something either fundamental or practical, or something which makes the knowledge cycle complete. It's something which I'm not very happy if someone says that okay, theoretically it can be that, but that doesn't make the cycle complete. Means unless you have a phenomena which is understood both theoretically as well as what is practically or experimentally you observed. so then it's only partially known, which will probably not be very satisfactory for you to do what you do. So that's
Do you feel that there is a difference in the culture of research as a whole with as the geography changes, like the culture of research in India might be different towards how it is perceived or conducted in France or Italy or the West Europe or Singapore? The in general, does research and its perception change with the geographical demography?
yeah, it's interesting the way you ask this question, because definitely it's not just research, but for getting anything or any work, uh, the culture of a place, or as you put it, geography, plays an important role. Definitely means, that means, in a place, someone will be interested about getting something done within the time limit. In another place, means I'm not now particularly distinguishing between one place or another. In another place, it might be that how uh, good quality your experimental data is, that in the sense that whether your signal to noise ratio is very high, that is given attention, rather than the qualitative understanding of your intuition and the experimental result. In another place, it might so be that you are more interested about the curiosity driven research done than worrying about its practical implications. So it depends whether you are in Singapore, in US, or in Europe, or in India. So I'm particularly refraining from stereotyping which country or which region of the country does what. But I have noticed this. There is no denying that this happens. But at the end of the day, when the scientific motivation is at the forefront, then these different cultures or getting things done in a different way does not matter too much. Even if, for example, it's somewhere in Europe, but people might work from China, India, US, and even within Europe, maybe Germany and French. So everyone might work in the same lab, and working style of everyone will be different. Someone will be particular about what will be the time during which the work can be done, and so on. But if you realize that that is the part and parcel of the development of a person, and by the time researchers actually start working together, they are already relatively old. They are in their 20s or 30s, so they would have had their characteristics which are already developed. So if your question is that whether there is a clash of the different styles of working, yeah, that also happens. I mean, I cannot say that that doesn't happen, but a short answer to your question is that yes, definitely there is an effect of different cultures and the way they get their research done, and which is a good thing rather than a bad thing, is what I feel.
But okay, particularly if we talk about India, what do you think are the things that we are really good at, and what are some aspects that we can improve at?
Yeah, so simply the answer is probably cliche, that in India, theoretical research people are really good at. Means there is a lot of uh, kind of interest also to do particularly theoretical work and so on. The aspects where our country can grow and grow very fast is where they can actually also balance with both theoretical and experimental work, because this is absolutely necessary. Means we cannot have a country with a large number of theoretical physicists who are proposing or even calculating things which is not getting done in the country, or there are very few. And then at the end of the day, one has to realize that it is the responsibility of, at an institutional level and definitely at a country level, that if there is some theoretical development or experimental development, that people work practically in house. Because though there has been a lot of talk about with the possibility of online discussions and so on, my personal belief is that the experiment, theory, work, collaboration together happens the best when people do have an on-site or in-house discussion. Means I would really like that in another generation our country does a lot of experimental work, and many which might even be translatable to practical devices and instruments. But this is happening to some extent, but I hope that it happens faster.
In the past 10 years or 15 years, what do you think has been a breakthrough of sorts in the domain of physics in general? And what has been its implications? What will be its future scalability, scope of future scalability? And the second part is, what do you think is a domain or area which has the greatest chances of breeding a breakthrough in the upcoming decade or two?
Yeah, so if you ask such a broad question, that what has been the breakthrough in physics in general, because there had been a lot of breakthrough which is happening, and practically on an every year's time scale, you see Nobel prizes are actually given for the breakthrough in physics. For example, there had been discoveries of Higgs boson, there has been gravitational wave discoveries, there had been incredible amount of progress in the astrophysics, condensed matter physics, and many other areas. While my opinion, if you ask, it will be a bit biased, but I feel that the progress in the domain of quantum technologies in general, for example, utilizing the concepts of quantum mechanics for practical uses, especially in the domain of quantum computation, then quantum sensing, an area which I absolutely didn't talk about. For example, you can detect tiny magnetic field using these atoms and many other platforms. These, for example, nowadays we can have clocks with stability of 1 part in 10 to the power 18 or even better. So that is actually used for development along the direction of global positioning systems and many other areas. So I am really impressed by the development of this field, and which by no means is a concluded field. So it is ongoing. So in the past decade or so, the development of quantum physics in general is something really nice. And in another decade, if you ask me, an area which I am keenly studying and feeling that there will be an interest in this is the development of this artificial intelligence, the so-called AI. And then there are even proposals of merging the idea of quantum related studies and artificial intelligence and so on, but that is probably too speculative, and many people believe that it may be even farther away. But the development of the area of artificial intelligence and large language models, which many people thought was not even physics a few years back, and even this year's Nobel Prize, many people would probably say that, when you are actually awarding this, but this is incredible. And then in many areas of physics, the uses of the machine learning, artificial intelligence is making the progress much faster. And of course, there are associated risks as well, but there are other people who will be better at explaining that. But I feel that this is a direction which will probably be a direction to watch out for, especially if there are younger people who should concentrate and study on the development of quantum technologies, and then try to merge. And another philosophical progress which I feel have happened is that there are many interdisciplinary research nowadays. For example, the boundary between particular research where someone is doing this laser cooling and trapping of atoms, and then looking at the molecule formation at the very low temperature, getting into so-called quantum chemistry, and then having these techniques to trap and cool atoms using optical tweezers, and then applying it to large molecules, even DNA and so on, looking at the properties of that, and creating machines like quantum sensors to actually trying to detect the brain activity without having to drill a hole inside the brain, just by looking at the magnetic field profiles which are created. So these are at the boundary between the physics, biology, and chemistry, and many of these researches are now becoming the forefront. And earlier days, someone who would be a physicist would say that why would I have to learn about chemistry, or vice versa, or something like that. But now this is a healthy sign that this is happening. People are, for example, another area what is good is that there is a lot of uh, spreading of awareness of what is happening in the labs and research groups, for example the podcast and so on. And these interdisciplinary approaches are actually going to be helpful, is what I feel. And not even that I'm hearing now, not at a technical level, because I'm not capable of understanding that, even the financial calculations, and people are interested about the fintech to be using various quantum technologies for predicting the financial models, etc. So these level of interdisciplinary research is also going on, and I feel that in another decade it will probably uh, make the make the research not particularly focused at one isolated area of physics or chemistry or biology, but make a broad impact. So this is another change what I have seen over the past, I would say, decade or so.
Okay, again a two-part question, but has AI influenced your workflow as an experimental physicist? If yes, what has it been able to contribute to it? And the second part of the question being, how do you see society after we have reached the zenith in regard to the artificial intelligence technology, like that state of achieving the super intelligence or even the quantum machine intelligence, because you talked about that speculative theory of combining the two. So that uh, both these parts.
Yeah, so in a way, the experimental physics getting influenced by AI in the context of my research, I would say that has not happened as such, though we have done some work on this image analysis of this ultra cold atom cloud using some machine learning algorithm, which is kind of well known in the community of not so much AI but ML, the machine learning and so on. And since those algorithms have been already available and papers have been published, we used it, which was nice, useful results for us, which actually affected in a positive way. Another thing what I see is that quite a few of AI, or especially the large language model, which is mostly coming bundled with your computer programs and so on, improves the quality of the writing, especially at the level of grammatical errors and so on, which is nice because when someone is communicating, unless someone asks the program to write the entire report, which is not something nice. But on the other hand, if the quality of a short report is good, what I get to read, and that grammatically pristine report can be attributed to the uses of some AI, then why not? Which actually helps you to understand the communication fast. So that way, there are some positive effect. The second part of your question is very difficult to answer. For example, this is the kind of question which probably people worried about in 1950s, that whether nuclear energy will destroy the earth, whether AI will take over and destroy the humanity. So probably yes or no, but at least as far as nuclear energy is concerned, that didn't happen. But I'm sure that people said after the first few nuclear tests that one day the entire earth will be wiped off because of some nuclear bombing. So that what will happen is something will be very hard. We will probably see what is going to happen in another 20, 30 years. But I'll stop here on that question.
Okay, due to the paucity of time, there are two. I'll like for you to at least touch upon these two theoretical aspects. First one being quantum sensors, which you briefly mentioned, and that in regard to how ultra cold atoms they can be utilized to create highly selective quantum sensors.
There had been a huge amount of work which has happened. Even in our lab we had demonstrated quite a few results in recent past. So one obvious sensing technology is sensing of very tiny magnetic field. For example, as I explained, I think in one of the previous discussions with you, is that an atom can be thought of a tiny magnet, the tiniest possible magnet. And like any magnet, in presence of an external magnetic field, it precesses around the magnetic field, and the precessing happens at a frequency which is known as Larmor precession frequency. And then there is also another known concept. If laser light or any polarized light is sent through the medium carrying these atoms or tiny magnets in presence of external magnetic field, the polarization state of light gets rotated slightly, and that is known as Faraday rotation. And one can measure this Faraday rotation with an extremely high precision. So that means this Faraday rotation is kind of proportional to the external magnetic field. And just by measuring the probe light which is passing through a region where these atoms or atomic spins are precessing around the external magnetic field, is enough to measure the sensitivity of the external magnetic field at the level of femtotesla per square root of hertz. So that means, over a second, if you make a measurement of such a system, you will be able to detect a magnetic field fluctuations of the order of 10 to the power minus 15 Tesla. So that means, far, far less than even stray magnetic field due to Earth's gravity and so on. So now, one application is that if you want to detect a small change in magnetic field, if you take such a device along, if there are some mineral deposits or something like that, so you should be able to detect it very well. So you can also use it for defense purposes. You can use it for detecting any biological changes, because most of these biological processes includes some tiny current passing through your brain, for example, and they create a small magnetic field outside your body, and that can be detected to know about whether all the biological processes are going all right and so on. So applications in biomedical and prospecting, mining, defense, and various other techniques. So last couple of decades actually saw enormous progress towards the sensitive measurement of magnetic field as well as electric field. So that's another technique. And electromagnetic field, for example, radio frequency, for example, any radiation that can be detected and so on. So I would say, if you ask me, that quantum sensor technology is a far more matured field than people actually normally realize. And many of these devices are either getting deployed with miniaturized form or at the process of getting deployed. So I am very hopeful that in another 5 years or so, we will see a large number of quantum sensing devices which someone can even probably buy for their own uses and so on. So that is technology which is promising. And atom based quantum sensing is the most promising, because the noise in making these measurements are extremely suppressed in case of atoms, because when you can isolate a single atom, or having an atom which is not getting affected by the environmental disturbances or collision with other particle and so on, then the sensitivity of such a device is actually at the so-called standard quantum limit. So that means, we means as a whole, the research group and the companies who are developing these sensors, so they are actually developing this sensor at the level of the what is limited by the quantum Heisenberg uncertainty principle. So this is something which is really incredible. So quantum sensor technology is one of the happening areas of research, is what I will say. And may I say that quantum sensors using neutral atoms are the most promising, and also being used, and many people even say that the atom based quantum sensors are the gold standards in quantum sensing. So this is also another way of saying that how lucrative the research direction here.
No, most definitely, actually. Quantum sensors may be in studying quantum biology, which
Mm-hmm.
wasn't possible before the advent of quantum sensors.
Correct.
As brilliantly as we are able to study it now, then even you did mention a few minutes back about atomic clocks. It's
Yes.
used in those. Then even to the extent of measuring gravitational waves.
Yes,
So,
of course, the gravitational waves are measured in a different way.
hmm, hmm,
That is measured using a very large interferometer.
hmm, hmm.
The presently existing gravitational wave technology, and we must be very proud that India is going to have their own gravitational wave detector also very soon, because government of India have also approved a very large scale project to develop an Indian gravitational wave detector as well. And the principle of all these gravitational wave detectors are that they are essentially Michelson type interferometer, and then the optical interference fringe shift because of a gravitational wave is what is measured typically. And so they are, as of now, there is no use of atoms or cold atoms as such, but there are also proposals that in next generation there will be an integration of these ideas between cold atoms and these things, uh, gravitational wave detectors. Yeah, but that's also another incredible research progress over the past few decades, which culminated into the first detection of the gravitational wave not so long ago. And this is also another impressive area.
yeah, I mean, quantum technology is finally starting or is uh, beginning to see its area of applications and implementation and penetrating that industry domain.
Hmm.
But
Yes.
okay, moving a bit forward, would you please talk about quantum criticality and what do we get to know from it, how we understand it, and in general how we the techniques or the methods that you use experimentally to explore new quantum states or phase transitions and the interaction of matter in general.
Yeah. So again, this is a uh, this is a word or a terminology which is used in various contexts, the criticality and so on. So one way is, for example, very simply, one critical behavior, or in the kind of research where we do is that so-called critical temperature or something. So where, as I was explaining, that when you have these atoms which are all moving around, and they are mostly showing the classical statistical behavior, and as you know that there is nothing called classical physics or quantum physics, there is any boundary as such, because everything at the end of the day finally is explained by one single uh, statistics or other. But however, what happens, there are certain measurements, for example, how many atoms are occupying the absolute ground state, or so-called overlapping wave functions and so on, proportional to the total number of atoms available in your trap. So that kind of quantity shows some critical behavior at certain temperature. So for example, if the temperature is higher than that, for example, typically it's of the order of 300 nanokelvin for a certain type of atom, rubidium atoms in a trap or something. So above that, we would say that it's a normal or thermal gas. And then if your temperature is far below, like 10 or 15 nanokelvin, then you will say that it has crossed into the quantum domain or quantum type of measurement. So this is one way of looking at criticality. Another is that, for example, suppose you have this quantum mechanical objects, these atoms, they are trapped in some kind of a periodic array created by an optical lattice. So that means an interference pattern of light where the atoms get trapped in the intensity maximas, and the same way an optical dipole trap work. But here, since it's a periodic arrangement, we call it optical lattices. And then in case the atoms are in lattice, there are ideas that an atom can move from one lattice side to another lattice side, but not really classical way of motion. It's more like a quantum tunneling. So now the tunneling from one well to another, this trapping geometries, they are considered sometime as a well. And then it has to be competing with the interaction energy between the atom. For example, two atoms, when they are on top of each other, they do interact, and the interaction can be because of various reasons. One obvious way is that there can be van der Waals interaction, or what one says about S wave scattering, and many other waves of this interaction. So there is a shift in the energy level due to the interaction as well. But now, if you look at this physics of the tunneling, that means an atom goes from one side to another, and the another side was already occupied by another atom. So now there will be two of them. So whether they would like to go into this configuration, or they would like to happily stay in two neighboring sides, so that is decided by the critical interaction strength or critical tunneling probability. So there are some critical phase diagram where one can actually go from a situation where all the atoms are kind of tunneling from one side to another. That is typically known as superfluid, because they are fluid. Or if they are all pinned to their respective energy or lattice sites, then they are like an insulator, because they are not moving this atom. So then there is a phase transition between the superfluid to this kind of insulator, what is known as a Mott insulator, thanks to the physicist Neil Mott, who actually discovered them. So that is also one example of this kind of behavior, of critical behavior. And there are many example in the field of quantum physics, particularly taking into account the atoms which play the role of electrons in solids, for example, where you do have phase transition in quantum dominated regime, where one says that there is a quantum criticality which is happening. But of course, this term depends on the uses and context in many cases. So I gave you some examples where I would rather use the term quantum phase transition or quantum phases uh, more comfortably than to put them under this broad class of physics where one says that quantum criticality and so on. So that will be the approach.
Okay, so this is a segment that we do on the show. Dr. Chaudhary, what is your word to humanity at large?
Yeah, so I think, particularly for scientists, we have an advantage that there is enough excitement which can keep us occupied. And I hope that in every profession, people find that what keeps them really focused, what they like, even if it is not a profession, if it is a hobby or something. So in that case, there is no conflict in humanity, because if everyone is doing what they like, there is no point telling that you don't do that, or you don't do this. So it is good, because at the end of the day, I believe nobody would like to do something which will eventually put humanity in danger. So means the danger happens only when people get involved into doing things which they don't want to do or something like that. So it's perhaps best that not getting involved into things which are not someone's passion or something like that. So that will probably be good for humanity. Then progress will happen in a very coherent way, because everyone will be focused on doing something. Because I personally don't believe there can be someone or something which will say that the focus is to destroy the humanity or anything like that. So of course, it is difficult to solve all the problem at the same time, but trying to solve all the problem at the same time is even more dangerous. So that's why it's best that one should do what one is most happy doing. So that would be my 2 cents on it.
Dr. Saptarishi Chaudhuri, thank you so very much. It was a lovely conversation and a delight to talk to you.
Thank you. It was very nice. The questions were very nice. I hope that it will be useful for you or
Most
the
definitely,
listeners.
most definitely. Everybody who will be watching this, I'm pretty sure they'll be taking something away from this, in the scientific sense or even the more general life wisdom, that kind of sense. But yes, thank you so very much.